We're going to jump into our next speaker. Let me just, I don't even have a pen. Yeah, I do. All right. Our next speaker, we can go over his accolades, or we could say that he is the one who correctly predicted a bunch of the past elections when no one else predicted it. So he got it right. Oh, that's too much pressure, sorry. So everyone please welcome the Bayesian, Andrew.
Yeah, I didn't predict the last election. Well, we said that there was about a 50-50 chance of the two candidates winning, which I think was a reasonable summary. I was having some discussions with people after that. People were talking about the relative merits of analytic or statistical election forecasting and prediction markets. Sometimes people said like polls versus prediction markets, but that's not really right because the polls are inputs to all of these things. The prediction markets use polls as do models. And it struck me that there are settings where prediction market will work much better than a statistical model, and that's situations where you don't have a lot of past replication. So for example, a candidate dropping out of the race, this is not something we have data on, and it's going to be very hard to incorporate that into a model. It makes sense to use a prediction market there and do your best. Another example would be a poll comes up that's unexpected. So before the 2024 election, shortly before, there was a poll from Iowa that had an unexpected result. The prediction markets kind of choked on that. It's hard to handle that, but the models worked fine because that's exactly what they're designed to do. Unusual polls happen all the time. It's a little like this famous example where they ask people to estimate the weight of the pig at the county fair or something like that, and they guess it, right? That's fine, but if the task were multiply these 5 two-digit numbers, I'd probably rather use a calculator. So in that sense, statistical inference is like the calculator. We want to put more problems into that setting. In the same way that we no longer need to talk about the gods throwing down thunderstorms, we can talk about air masses. We'd like to enter things into that, but we're never going to completely be there. The previous talk was fascinating, and I was thinking about the comment at the end about uniqueness and the idea that we should each have our own personal brand. And I think there's a lot of truth to that. Like we live in a high-dimensional space. You might say, how can 8 billion people be unique? But of course they can. And anyone with more than one kid knows that how possible that is, even with people who share half their genes. In statistics, though, it's a slightly different attitude. Statistics is the science of defaults, and any method that we do, we'll do more than once, especially for me because I write textbooks and we write open source code. But even if you're only working on one problem, you're really developing a method that's supposed to work in multiple cases and scenarios. Brute force is the goal, and this is kind of a math attitude. So, mathematicians, there's kind of two kinds of mathematicians. There's the kinds who want to be clever and the kinds who go for brute force, and I'm the brute force approach. Like the cleverness is figuring out how to apply a problem in brute force. In statistical theory, there's a term frequentism, which refers to studying the procedures of properties of a procedure that's done repeatedly. There's also a term Bayesian inference, in which a statistical method is evaluated based on averaging over a prior distribution. That's the same thing, actually. Bayesian and frequentist statistics are identical. They're both about replications, and in both cases, the replications are often only mathematical. And the other thing was that I found very interesting about the previous talk was the discussion about the evident utility of chatbot tools and related, and the question of where the data come from that feed into them. Now, I don't have any insight into chatbots. I'm too old for that. But I have insight into statistical models. And for me, the input are the applied problems that I work on. And I guess I've worked on thousands of problems, and so there's a kind of internal replication right there. I guess I'm running a chatbot on myself in some way. Now, usually when I speak, when I give a talk, I like to start with just whatever, like on my way over here was in my head, like some difficult problem I was working on, and share that. So I thought I'd do that. I have a horrible feeling these are, I don't know, like I haven't been working on a lot of little applied problems so much lately, which is probably bad for me. Like you have to continue to refill the well in that way. So I think one or two of these I might have even talked about at a previous one of Jared's conferences. But I'll tell them quickly, and then I'll give you the main theme. So the title of the talk is What's Going On in There? Bayesian Tools for Understanding a Fitted Model. And I won't talk so much about Bayesian tools, but about the concepts of Bayesian workflow and how they apply more generally to statistics or data science. So the first problem is estimating the rate of exposure. So there was a survey done in 2020 where they, in Santa Clara, California, where they gave a bunch of volunteers, 3,000 volunteers took COVID tests, and I believe this was the sort that would be positive if you had ever been exposed to it. 1.5% of the people in the group sampled had COVID, and or tested positive. So that would suggest a crude estimate of 1.5% of the population there in that county. They did some adjustment though, because who knows who's going to come in. There were more people. This was the county where Stanford University is. That's who did the experiment, the study. More people came from near Stanford than from away from Stanford, so they did a geographic adjustment, some demographic adjustments. After doing that, they estimated the rate as being somewhere between 2 or 4%. Well, that's not quite right because the tests are wrong sometimes. Actually, the rate at which the test gives the false positive rate of the tests are very low, maybe 0.5 percentage point. So then you'd say, well, the estimate was 2 to 4 percentage points. You subtract 0.5%. You can do that statistically, and they got an estimate. However, their estimate didn't account for the uncertainty in the false positive rate itself. That itself was being estimated. And so then when we do this, we get a wider interval, which included 0%, by which I did not think that the rate was truly 0%, merely that the data were consistent with all false positives, which of course wasn't. But there was a lot of uncertainty, and that had policy implications. If they had really known that 2 to 4% of the people had already been exposed by that time, by April 2020, that would have been very informative. Okay, fine. We published our method. It got published unusually for academic publication. It got published that year in the journal, and it was in a preprint. And some people in Australia did the same thing. They had a study in Melbourne, Australia. It happened to be about the same size. And so they followed our procedure of first adjusting for the possibility of false positives. You can also have false negatives, but the math of it is that doesn't really matter when the prevalence is so low. So you can put that in your model too. It's not going to make a difference. So first they did that, and then they adjusted for demographics and then geography, and they had the data by postcode. It's charming Australia. The postcodes are just 4 digits long. Here they're 5 digits. In China they're 6 digits. So there's orders of magnitude happening here. This was just one city there. So they also had about 1.5% had it. It was from the same year. It was from early 2020. After doing the adjustment for the false positive rate, our best estimate was about 1.2%, I think, 1.1% with uncertainty. Then after they adjusted for demographics, it went down to 1%, about 0.9%. Then after they adjusted for postcode, it went down to 0.7%. So it's like the more adjustment they did, the lower the estimate was, which, like, I don't know what to think about that because it seemed wrong. On the other hand, of course, that's the point of doing an adjustment. It could change things, right? So we have two hypotheses. One hypothesis is that the sample was non-representative in some ways that were adjustable, and the real rate was lower. The other possibility is that there's some weird thing going on with our statistical method. And I was worried that it was possibility number 2. Now, before getting to that, let me go back to Santa Clara, California, and say that the people who were living further away from Stanford were more likely to test positive, which was why when you do the adjustment for geography, their estimate went up. But there's some interactions there because our guess is that the people who would go from far away to get tested are more likely people who might have been concerned about being tested positive, whereas the local people could very well have been the worried well who were sitting there and it was right at Stanford, so why not get tested? So it's an example, not where statistical adjustment is a bad idea, but where you should think a bit about what your model is. And that's, yeah. So some of that could be addressable from the data, but they didn't do that. So to go back to the Australian study, what did we do? Well, we simulated replicated data from the model. So we fit the model and we simulated a new set of 3,000 people, 3,000 tests, and ran our thing and did it. And we found that when we did, we did a simulation in which there were no effects of geography or anything else. So the adjustment shouldn't matter. Or no, sorry, not that there were no effects. We did a simulation in which the people were a random sample. So adjusted, there can be geographic effects, but adjustment should in expectation have no effect. When we did our procedure on our fake data, the same thing happened. The estimate kept creeping down. And so then we knew it was a statistical artifact because it shouldn't happen in that simulated setting. And so we sat there. Well, short term, the paper, we talked to them about it because they said, we're using your method and it's giving this weird result. And this was before I thought about doing the simulation. But I said, I don't believe it. I don't believe our method. This is suspicious, so just do minimal adjustment. So that's what they did. They published it. But it was eating at us for 2 years. We're doing simulations, trying to figure out what was going on. We finally figured it out. And now the next step is to figure out how to do better in the future. Well, raise your hand if you know any kind of Bayesian statistics at all. Okay, so half of you will enjoy this next 5 minutes, and half of you will be like, yeah. Okay. Okay, what's going on? So let's think about the model. So the model is inherent. Oh, well, I'm going to tell you a principle of statistical computing. It has 2 halves. The first principle of statistical computing is that all mixture models are hard to compute. It's just true. But mixture models have an inherent discreteness, and discreteness makes computation difficult unless you only have a few things and you can count them. The other half of this is that all computational statistical problems are actually mixture models. That causes them all. And this is an example. It's not formally a mixture model. It's a hierarchical logistic regression model with an adjustment for testing error. Okay. So we'll get to that. Okay. For each of the models that we fit, we could look at the posterior distribution, your uncertainty about the prevalence, which is your quantity of interest. We made a scatter plot of the prevalent, for each dot in the scatter plot, it's not a data point, it's just a draw from the posterior, so it represents a posterior distribution. We make a scatter plot of the prevalence versus the false positive rate. Now the prevalence we know is somewhere between like 0 and 2%. The false positive rate, we have data on the on that, and we know it's going to be also around 0 to 2%. Just, it doesn't have to be the same range, but it roughly is, or maybe 0 to 1%. And you fit the first model, and your estimated prevalence is around 1.1%. Your estimated false positive rate's about 0.5%, which is why it went down by that much. And let's think about the correlation between them. The correlation is negative, right? Because the lower the false positive rate, the higher the prevalence. Like if the false positive rate were 0, then the estimated prevalence would be 1.5%, which is what you see in the data. If the false positive rate were high, like 1%, then the estimated prevalence would be down at 0.5%. Now, from the data on the, are you kidding? That is so cheating. For one thing, that's not chalk, and for another thing, it's cheating. Okay, the persistence of vision. We know the false positive rate's essentially between 0 and 1%. I mean, because we have enough data on laboratory tests. Okay, so what happens is that as we add more things to the model, we start moving down this curve, and we get lower estimates of the prevalence and higher false positive rate estimates. In fact, if we run our model and said we knew the false positive rate was 0.5%, we wouldn't have the problem. So what's happening is when we load up more features in our adjustment model, we end up pushing our estimate of the false positive rate higher. Okay, so then we have to figure out why this was going on. So this is really a complicated procedure, like a real detective work, trying to figure out what was going on. Now here's the mixture model. Suppose you test, in this model, if you test negative, you were never exposed to COVID. I mean, it could be a false negative, but again, that's given the prevalence is low, that's essentially can be ignored. If you test positive, there's two reasons. You could have tested positive because you got bad luck. You had been exposed to COVID, or you tested positive because the test was in error. So it's a mixture model. You're implicitly, if you're fitting a Bayesian model or any probabilistic model, you're implicitly assigning each person to say you're one category or the other with certain probabilities. Now, let's imagine only one of the two mixture models was correct. So under the false positive model, everybody has the same probability of having a positive result. It looks completely randomly distributed. Okay? Under the alternative model, which includes, well, what's the probability of having COVID, having been exposed to COVID? It depends on the coefficients in your model. If you're doing no adjustment, it's just a straight probability for everybody, and that works. That's just there's a probability of having it, probability not. But now suppose the probability of having COVID depends on your sex, your ethnicity, your age, and your postcode, which certainly should to some extent. Then what you would see is a probability that varies more by person. Now, this is statistics, right? It's Bayesian statistics. It means you have to distinguish these two hypotheses based on the data, right? In particular, you want to estimate the aggregate proportion of cases that are random, false positives. So you imagine a landscape. So imagine you divide the population into thousands of post-stratification cells, like young women who live in postcode number 1, middle-aged women who live in postcode number 1, old women who live in postcode number 1, young men who live in postcode number 2. So we have maybe a couple thousand of these cells. We might even have more cells than people because we only have 3,000. A lot of the cells have 0 people in them or only 1 or 2. Some of them might have 10 or 20 people. Under model 1, which is false positives, that's the one half of the mixture model, we would expect these to just be random. So it would look like the number of positives in each case would just look like random numbers sampled from a binomial distribution in each case, which would mean like a bunch of zeros and ones mostly, because after all, the cells mostly have 0 and 1 people, and even the ones that have a lot of people might have 20 people, and if the probability is only 1%, it's going to look like 0. Now, what about the other model? Well, the other model, the distribution that you would expect to see in this landscape depends on the coefficients. So if the coefficients of the adjustment model are large, meaning that postcode, ethnicity, et cetera, are very good predictors of whether you had it, then you'll expect the probability to vary a lot from cell to cell. So there might be some cells where the probability of having been exposed to COVID might be 15%, and others where it's close to 0. It has to average to a small number, though. If you have to average to less than 1%, in the order of 1%, then only a few cells can really have a high probability. And they might not be highly populated cells, which means, well, what it's telling you is that it's going to be very hard to distinguish between the two models from the data, because either way, you're going to get this kind of dispersed pattern of random seeming people having COVID. Now, which is fine, but when you do this is where the Bayesians in the room will perk up. To figure out to estimate the probability of the false positive rate, basically the probability of the two mixture components, what you need to do is figure out what's called the marginal likelihood of each of these two models. And the marginal likelihood of the false positive model will become higher than the marginal likelihood of the other model, because the false positive model knows exactly the probabilities, and the other one has to average over a broad distribution. And this is related to something in statistics called the Jeffreys-Lindley paradox. Now, I'm explaining it in a very convoluted way because that's kind of how we came to it. But then the question is what to do, because we actually do want to make an adjustment. So what's happening here is not just that, oh, we did this adjustment and things are off. The issue is the more adjustment you do, the more this artifact happens. And so you don't want to use a statistical method that has an artifact like that. So the short-term answer is you do simulations, simulate data, estimate the size of the artifact, and then do a kind of post hoc correction. So you can say, look, when we adjust for this, we want to adjust for these, but when we adjust for this many factors, it will systematically reduce the estimate, and so we need to kind of jack it back up. And that's very horrible. Also, it seems kind of anti-Bayesian, like I'm using, so Bayesian inference is always optimal averaging over the prior. And so if I think it's giving a wrong answer, that means that I'm not interested in averaging over the prior. I don't believe the prior. I have this vision of a Bayesian statistician as being like, a Bayesian statistician is some person in a room, or maybe I should say an AI agent in a room, some sort of entity in a room that has just an inbox and an outbox. And the inbox is people give data, and the outbox is the Bayesian gives out inferences. And the Bayesian has to use a prior. The prior represents a distribution of true values of all of the data that might come into your inbox. So I would say, well, I don't think I believe this prior. I wouldn't use my method in this setting. Why would I not use this method? Because I was trying to be kind of, safe and conservative. So we used weak priors on these regression coefficients. And if you use a weak prior, that means you're allowing the regression coefficients, the adjustment factors, to potentially be very large. Now, they won't be very large in the data because you don't have a lot of data there's not really evidence in the data for that. But because the data are weak, when you use a weak prior and you don't have a lot of data, your posterior will be kind of broad. We don't usually think about that because the adjustment is just a means to an end. Right? If I lived in a world in which the factors such as age, ethnicity, sex, postcode had huge effects on your probability of exposure, then I would want to use the model we used. But in that situation, that would probably slap you around the face in the data. Like, for example, what if you saw what if you found that 50% of the COVID cases were all in one postcode? Okay, we don't see that, right? But we don't expect to see that, and our model, by accounting for that possibility, which we don't expect to see, that model actually somehow forces the inference to it causes the estimate of this half of the mixture, this part of the mixture, this mixture component to be lower. It's very unsettling. it's an upsetting example, as you say. So the part we haven't really figured out is, well, what's the model that we should fit that wouldn't have this problem? It's sort of weird being in this halfway point. But I think it's important, and it's not, there's no alternative, right? It's not like I can say, oh yeah, just take the raw data estimate. Well, if you do that, it's obviously wrong because you're not adjusting for the false positives. Let's just take the point estimate of the false positive rate and just use that. Well, that wouldn't be so horrible here. All the problem is occurring from the uncertainty in the false positive rate, because that moves you along this scatter plot. But that wouldn't have worked in our Santa Clara, California example, because there the uncertainty in the false positive rate was vital to our understanding. And so I don't think we have a great alternative answer here, which is kind of funny because it seems like a pretty straightforward problem. So maybe next year I'll tell you how we solved it all. Who knows? Okay, so again, I connect again to the previous talk, which I really enjoyed, which mentioned the jagged frontier. And I think that the problem, I think, is it's like you have this feeling like we don't know where we are, but sometimes it's almost the opposite. You know where you are, but you don't know where the frontier is. So you don't know where you're standing there. And I think this comes up a lot in programming as well as data science. So they say that, like, what makes beautiful code? What makes code beautiful? Say, like, oh, it's a minimum number of things, or say, no, code that runs, that's beautiful, right? But that's not right. That's not right. Code that runs and you know it runs is beautiful. Oh, there's other things too. You might want your code to be easily modifiable by others and so forth. But that's the hard part, right? Is knowing that it's going to work. I mean, our model fit the data, seemed to, but then we had these problems. So our goal is to better understand the weaknesses of our fitted model and ultimately to learn more from data. And I want to just give you a little bit of an analogy. So imagine you're writing a paper, or you're giving a talk, you're giving a presentation, promoting some great new idea. So you need to answer the implicit question, if this is such a great idea, how come it hasn't been done already? That's really important. That sounds silly, but I've seen so many presentations and read so many papers where no one answers this question. It's like, our method is great. It dominates these other methods. It's just better, right? Well, that is wonderful. Why don't I believe you? Because, well, for one thing, I probably want to know where your method is worse. So I always tell people that if you want to convince me your method is better, I think the first thing you should do is show me where it's worse. Right? Now, that can be just a rhetorical trick, like, oh, the other method's great in that horrible situation we're never in, right? But that's part of what we do, again, thinking about statistics as the science of defaults, is we need to delimit the frontiers of where our methods work, and one way of doing that is to identify places where it gives bad answers. And people do not always do that. Right? So the first thing is just to say no method dominates, right? There's always places where it's going to be worse. But then suppose you've done that and you say, well, in this scenario, our method's better. How did it happen? And here's a bunch of possible answers. Everyone who came before me was an idiot. My method was out there, but it was suppressed because it was, the corrupt system would not let my method be out there. I mean, this happens sometimes. I'm not saying it never happens. It's a possible answer. Another answer, which is maybe a little more appealing, is the old method was fine in practice. There was no practical need for improvement, which maybe there still is no practice, or until blah, blah, blah. Another thing is computing costs. So yeah, the old method, I have that this new method costs more. It's more expensive. It takes longer to run. And so that's why people weren't doing it. But it's worth it, right? We're in a new regime. The old method worked fine, but now we're in the quantum regime. We're in the relativistic regime. Now, that's not so silly. That happens all the time. That old method worked fine, doing Mr. P is great, but now we have false positives, which we hadn't accounted for before, and that changes everything. We need a new method, right? So a lot of methods worked in the past, but aren't designed for future problems. My favorite example is classical statistics, which was developed in the 1930s to estimate things like what's the effect of a different fertilizer on an agricultural plot. But then people started applying it to things like medical research or education research, where you might have a very marginal incremental improvement, something that will help a small percentage of the students a little bit, or a small percentage of the patients a little bit. The effects will be small, and they're highly variable. We shouldn't expect to see statistical significance. Making decisions based on statistical significance is fundamentally wrong. I talked about that here, I don't know, 10 years ago, whatever. But that doesn't mean that what they did in the 30s was bad, or that those methods are great for problems where the effects are large and variation is small. Another thing is that it just is a new idea. Came up with this new idea, and it was motivated by some recent developments. So that's happened to me. I have come up with actual new ideas that I've published, and when I look back, I say, well, there was some old stuff in the literature that reminded me of this, but usually if I came up with a great new idea and it wasn't there before, you have to ask, why didn't people come up with it before? And again, I had a new idea to monitor the convergence of iterative algorithms in 1990, and it was new. And the reason why it hadn't been done before, I think, was because people had just been using iterative algorithms to solve problems, to kind of do a little better on problems they already kind of knew what the answer was, and they were trying to improve things. People already had approximations. Nowadays, we run iterative algorithms straight up. We just run them, right? But back in the 1980s, when people did iterative algorithms, it would be after trying every approximation that they could do, so they wouldn't be so far off. They didn't have the same motivation. As they started running them afresh, they had this problem of not knowing how to assess convergence. So it was a problem that people cared about, and that motivated the development of a new idea. So it wasn't that everyone before was an idiot, it was that they weren't motivated to solve this problem. Another thing is just there's a flat out new algorithm. So sometimes that happens. Someone comes up with a new idea, new algorithm, or new data, of course. That's a big one. We have new data, we have new computing. That's so many things you can say, and I'm sure I've missed a few. But I think that's kind of, some version of this is always going to be necessary. So where do I want to be in terms of statistical workflow? So I want to understand the models that I'm fitting. And why is that? Why do I want to understand a fitted model? It's not a completely empty question, because you might think, I'm fitting a model and my goal is to estimate the percentage of people who have COVID, or I'm trying to figure out the flow of some toxin in the body, or I'm trying to predict who's going to win the election, or whatever it is. I want the answer. So why do I need to understand the model? I mean, and I want to give a good answer. I don't want to be some sort of humanist. We always say, oh yeah, you need explainable AI because it needs to be comprehensible. People understand stories. No, like, forget all that. Like, I want to solve the damn problem. I want to make some money. I want to save some lives. I want to, whatever it is. Okay, so the reason I need to understand the model is because I don't believe the model. And my workflow is not to fit one model to data. My workflow is to fit many models to data and figure out what's going wrong. And so really two key principles here. So the first, and both are kind of different from how you often see things in a textbook, or at least in a Bayesian textbook. Maybe the non-Bayesian ones are better in some way. So the first thing to avoid is the idea that you only fit one model to your data. Now, you'll sometimes see, well, here's this paper, we fit the model, and there's some robustness checks. That's not fitting multiple models to the data. That's a rhetorical ploy to get you to, like, yeah, I mean, really fit multiple models. The second thing that I think is super important is that every method is applied multiple times. So we're not just attacking this one. We're not just attacking this one problem. And so understanding, so now what are the actual tools that get used? So just some tools that I'll mention briefly, R squared, like percent of variation that's explained. I've written a couple papers on it. It's a tricky topic, actually. The R squared is the 1 minus the residual variance under the larger model divided by the residual variance under the null model. In Bayesian inference, the residual variance under the larger model can be higher than under the null model, depending on your prior, so you can get a negative R squared. And I didn't like that, so we came up with a paper where we defined an R squared which is always positive. It has a cost, which is perhaps a benefit, that R squared depends on the unknown parameter values. So when you do inference, you get a distribution over R squared. But when you think about it, that's kind of right. You should have a distribution over R squared, because I'm not interested in the percent of variance in the sample that's explained. I'm interested in the percent of variance in the population that would be explained. And then further challenges come when we talk about multi-level models, and you want to know that I have a model, and I have state effects and year effects and state level predictors and year level predictors, and how much does this state level predictor explain this state level variance? That's an R squared like question. It can't literally be answered using that formula. It can really, I think, only be answered in a Bayesian or latent variable way. So that can be done. Another example is influence and sensitivity. So how sensitive is my inference to this one data point, or in time series, this clump of data points? It's a funny topic because there's a lot of literature on it, and each paper presents one method as if it's correct, but there's different things you can do. Just very quickly, there's one thing you can do if you're looking at influence of a data point is to say, what happens if I move the data point? That's the standard method of influence in regression. If I take the data point and move it up or down, how much does that change the estimated regression slope? And as you may recall, if you fit a linear regression and you have data here and here, and you move a data point up or down, these extreme points have high influence. The ones in the middle have low influence. It's not so simple, though, for something like logistic regression. So I have logistic regression. I can't move this point up and down. It's at 1 or 0, so I can flip it. So the influence of points in the extreme is much higher than ones in the middle, of course, because if I flip a high thing from a 1 to a 0, it can change everything. On the other hand, it's very unlikely that you would flip this from a 1 to a 0, because it's predicted to have, it's not supposed to be 0. So really, you should take your influence and you should probably multiply it by the probability that that would happen. And when you do that, the highest influence data points are not at the extremes or in the middle, but in between, in these kind of shoulder areas where they're away from the middle, so they have influence, but they still have a chance of making a difference. Now that's similar to a lot of things in life, right? Where if you're too far at the extreme, it doesn't matter, and if you're in the middle, then it's not influential. So that's moving a point. But another thing you can do is remove a point. So if I have a linear regression and I have a point here and I remove it, and that point happens to be right on the line, it'll have no influence. It won't change the estimated slope if I remove it. This is kind of weird, but is the case. On the other hand, it's kind of unlikely that that would happen, because if you shouldn't be right on the line, it's an unlikely thing. So if you average over the prior, then that should not occur. Another example is the equivalent sample size of the prior. Now, I was consulting once on a project where people were running regressions in order to estimate effects of treatments in their company, because they're trying to make money and so forth. And I recommended they use priors, and they already were using Bayesian stuff. And I said, don't just use priors on your estimated effects. Use priors on your coefficients in your regression for adjusting for things. because if you don't do this, you'll tend to over-adjust. Your adjustments will be based on noise. Then you can add more information. So they were doing this, and it was all working fine. And then they said, we had this case, and we had less data, and we didn't want our prior to have too much influence, so we weakened our prior. I said, oh, you fools, like you shouldn't do that, because the whole point of the prior is that when you have less data, the prior counts more. But of course, they were not fools. Maybe what they did could have been improved upon. The point was that they didn't fully trust their prior itself. And so one thing we started working on or thinking about, or I started thinking about, was how you can measure the size, the influence of the prior. And in a unidimensional problem, you can talk about the equivalent sample size of the prior. Like this prior is equivalent to 18 data points. But it turns out, for reasons that I cannot explain in the next 18 seconds, that in higher dimensional problems, it's not so clear how to do that. We're still struggling. I'm still working on that one, okay? But what I wanted to convey was that there's a reason why I want to understand our model, and there's a lot of tools that we're working on to do that.